My name is Aryaman, and today we are going to use DFT algorithm to find pulse rate of the PPE signal, and we will verify that those results with the previous proposed method of auto correction function. So what is DFT? DFT is nothing but a discrete Fourier transform. We already know what is discrete time Fourier transform. It is nothing but a Fourier transform of a discrete aperiodic time domain signal, which gives a continuous periodic frequency domain signal in a frequency domain, and DFT takes that frequency domain as an input, and frequency domain signal as an input, and gives the output uh, gives that output of a discrete samples of that continuous Fourier domain signal. So in simple words we can say in DFT, input signal is the output of the DTFT, which is continuous periodic frequency domain signal, and DFT gives discrete samples of the continuous DTFT signal we have got. So what's the basic formula for that we are going to see. So this is the basic formula where k is the index or the sample of that frequency, discrete frequency we have taken, and xn is nothing but our original time domain discrete signal, and this is a twiddle factor, which is e to the power minus j 2 pi upon n into kth index into n, where capital N is the number of sample we have in our frequency domain that we are going to take, and small n are the total number of signals that we have in our time domain signal. So in general, we will in this example we are going to take is that we will going to take that k is capital K, that is total samples in our frequency domain, and the original signal are equal, that is k equals to capital K is equals to n. So as you can see, formula is x k is equals to summation of small n from 0 to capital N minus 1 into xn into twiddle factor that we can denote by w n k to the power n, where w n k is a twiddle factor and small n will vary from 0 to n minus 1. So we can distribute these into a complex form, which is cos 2 pi by n into kn minus iota sin 2 pi by n into kn. So using this formula, we are going to implement this in a C or Arduino IDE. So what's the function we are going to see that? So this is a function that we have implemented. So we will take the real part and imaginary part differently and use those for our computation. So first I've calculated the real part and imaginary part using in a single iteration. So first I've taken a loop for the calculating it. This is the second loop for this is the loop for the small n, small k, that is samples in our frequency domain, and this is for the small n, that is 0 to n minus 1. As you have seen, as you have taken capital K is equals to capital N, so we are taking n in both the loops. Here small n is our total number of samples that we have taken, that is 75 in our case, and sample frequency is 25. So now going ahead, we will see how we will implement it. So as we know, we have an inbuilt function known as cos and sin in our Arduino IDE as an installed packages. So we will use that and implement this function in our code. So as you can see, this is nothing but a direct implementation of that, where is 2 pi by n is denoted by 2 pi and small n, and I and j is nothing but small k and small n. So it's easy to see, it's straightforward, and we are summing over every real part and imaginary part like this for j is equals to 0 to n minus 1. So as we have taken the real and imaginary part in different arrays, now We will use those to find our magnitude response, not magnitude of a discrete Fourier transform, not magnitude response. So by using inbuilt functions of power like in C and square root, as Arduino is straightforward like C, so we are going to use square root and power functions to get our magnitude, and this is the x magnitude, that is magnitude or DFT of discrete time signal we have taken. So now how we are going to find the pulse rate. So for finding a pulse rate, when we have a that frequency domain signal, we are going to find the first maximum peak we have got. That is, in a signal there is a case where we have a maximum peak that can be repeated, but we will take the first maximum peak as we want only up as that will repeat, so after that it will be periodic, so you will take the first maximum peak. So using that concept, we will use first maximum peak, and which is implemented by this for loop. We have taken kmax as a point for that peak index, and this is a normal maximum function we have taken, and I plus 1 we have done as in the frequency index, we will going from 1 to the index that we want, that is kmax. So from that we can use a pulse rate implementation, that is for in 1 minute, that is 60 seconds, into kmax into frequency sampling rate, that is fs, and divided by, and that is the total number of samples that we have taken in our domain. So straightforward, now we are going to implement see the results. As we have previously discussed about autocorrelation function, we are using same computation we have used in previous experiment, and before going to do that, we are going to pass a moving average filter, getting that output, and that means abstraction as usual we are going to do. So now I'm going to add the results. We will see the results. So as you can see, from autocorrelation method we are getting 71.43 pulse rate, and from DFT we are getting 80. So error is out of 9, which can be possible in a case as we have taken less samples. So it is a pleasing results, we can say. So this is the Arduino implementation of that method. As you can see, this is quite a headache for us, because for a large number this can be a this is a bit lengthy code. So we can use matrix computations easily. So for using that, either we can implement same thing in C using a two-dimensional matrix, or we can use a MATLAB to implement same thing. So here I am using a MATLAB code to demonstrate the same thing using a matrix computation. That is, in our case, W known as W and K. That is nothing but a twiddle factor. So now I'm going to use a MATLAB computation. So first I've imported a data using the given CSV file using import data function, imported data that we already have in MATLAB. Now and this is a we are going to do slice first, and moving average filter is nothing, same function, everything is same. As you can see, nothing is changed. So function is everything same. Just a twist is that we are going to take a weight matrix, that is nothing but a twiddle factor. As we discussed here, linspace gives us the discrete one step factors, that is 1 to n minus 1 0 to n minus 1 in steps, that is nothing but in our case small n and small k. This can be in small n and this can be small k, as you want. As you can see, these are the weights. So if you want, you can see the results what weights are giving. So we'll first run this. uh, so what are the weights you can see? the complex factors we are getting, which are nothing but the weight matrix or total factor matrix coefficients. So as you can see, this is of n cross n matrix, which will be multiplied with our filter output, that is y here, and capital X is the discrete Fourier transform results we are getting. So for taking magnitude, we will use just an absolute function that is built in the MATLAB, and we will see the results in our plot. And similar method we are using here, as you mentioned here, you can see that it is symmetry in nature. See, so we are taking the index till n by 2 only, so that we can get easily the first peak point rather than repeating itself. So for n so that we get the first peak point only, so we are taking it to the n by 2, and for kmax is equals to 4 we are getting it. So from that we are getting a pulse rate of, you can implement it again. So you can see results are same as we got in Arduino. This is 71.43 nearly, and this is 80. So we can verify that our Arduino results and our MATLAB results are same, as we have used the same method and it should be. So for seeing the plots we can use MATLAB very often. So this is our input P signal, and this is the smooth and moving average. This is autocorrelation function, as we observe that it is decreasing and it will repeat itself. So figure 4, as you can see, this is a DFT implementation. This is symmetric, and figure 5 is nothing but the phase of response of DFT discrete Fourier transform of Xn. So as you have got here, we got the two implementation of the PP signals pulse rate, verifying from MATLAB and Arduino both with our autocorrelation function. So this is all we have done in this experiment. So thank you. We will see in our next lab what we will do.